Thank you very much, Nadja. Thank you very much to the organizers for inviting me. I'm very glad to be here. I've never been to Formnext before, although I've been working on additive manufacturing for 15 years. So yeah, it's kind of a kid's dream come true. I'm very happy. I'm going to first use my academic cap to talk about architectured materials, which is really what's of interest for me. And in the second time, I will present a way to obtain those architectured materials that is not 3D printing. So yeah, a bit of an abrasive take at Formnext. A short course, a crash course on architectured materials. So I'm a materials engineer by trade. So for me, a material has a function. So we create materials to fulfill a function. For instance, a mechanical function. And if you take this example of a very classical airplane, you have different components, different parts that are loaded in different ways. And if you do your strengths of materials, your design mechanics, you end up with material properties and material property criteria to select the materials you want to use for this part. And those criteria depends on the type of loadings. So this is basic engineering. But this gives us a good way to kind of explore the space of materials. The space of materials that has been mapped using the HB methodology. And basically the idea is to be able to represent material properties as charts like this one, like a 2D chart in this case, with stiffness versus density. And if you do that, you can see that materials fills quite a wide range in this space. But there are some areas, some parts of this space that are empty because basically most of those materials, most of those properties depend solely on the chemistry, basically the nature of the materials, their chemical composition, the type of bonds they have between atoms. And they miss one very essential parameter, which is geometry. And so HB, with others, proposed to expand this material space by playing on geometry. So in this case, it would mean to go on the upper left corner, which means very stiff material and very light materials, to have enhanced properties for fulfilling some kind of mechanical function, in this case, making very stiff and very light components. To do so, the idea is to introduce geometry within the material and not consider that the material is just, Young's modulus and Poisson ratio that you put in your finite element software, which is usually the mechanical design approach to materials. Because nowadays, and Formnext is a very nice example for that, we have a lot of new advanced manufacturing processes to be able to play with geometry at the scale of the microstructure, at the micrometer scale, at the millimeter scale. So we can actually use all the knowledge we have from structural engineering at the microstructure level. And this is basically what architectured materials are about. So of course, functional performance is not, depending on geometry, is not really a new idea. If you take this example of a bridge, those 4 bridges have exactly the same function, going from point A to point B, but they have very different performance and efficiency. And basically, to finish with HB, he proposed this taxonomy of architectured materials, and as you can see, there's a lot of things that I'm sure you already know, like composite materials and sandwich structures, foams, things like that. And a specific kind of architectured materials, which is lattice-based materials. And in all those structures, the key point is that the overall response of the material is mostly driven by the geometry rather than the chemical composition. And this is especially true for lattice structures. So if you look at the literature of the past, let's say, 20 years, architectured materials have been all the rage. And you can find a lot of paper making a case of architectured materials being the best material ever, the most efficient, the lightest, the strongest, the stiffest. The only problem is that most of these papers, most of these materials, when they are actually produced, which is only a fraction of the literature, of course, let's say less than 5% of the literature, they are produced in labs at for academic purposes. This can take months, 6 months maybe, to make a sample. And of course, there's a big gap to be bridged between the academia and the industry. And as Nadja said before, I like when my research is actually applied in the real world. Yeah, so just introducing the second part of my talk. So those lattice structures and as a more general case, architectured materials are the holy grail of material science. They're the best materials you can think of, but they have been studied mostly theoretically. Their impact on the way industry works and on the economy is gigantic. They provide especially high value in aerospace industry, defense, construction also, and which is why you can see those materials. You can see lattice structures in space rockets or in specific buildings. And with Tetmet, we finally provided a process to make those materials at an industrial scale, which means for a reasonable price. Yeah. So we have developed this very efficient technology to create lattice structures that we can apply at different scales, from millimeter scale to meter scale. We don't need a 3D printer. You have very nice examples of fully integrated additive manufacturing systems and hall 12 and 11. That will need probably a room of this size to make an industrial scale production of lattice structures. We don't need those expensive metallic powders that are, they are expensive, and that's if you can buy them, because there are a lot of logistics issues there. And also, we don't use voxel-based manufacturing. We are not at a fixed spatial scale. So basically, we have a great process, very flexible, that can save you a lot of material and a lot of energy. And this is 99% less energy than additive manufacturing. So yeah, what is adaptive spatial lattice manufacturing, ASLM, sorry. So it's a kind of additive manufacturing process. It's based on the assembly of metallic or non-metallic wires or rods that are laser cut and welded together with a robot. And this is all supervised by an artificial intelligence, of course. Nowadays, everything is supervised by an artificial intelligence. And we are basically building up lattice structures. The process also includes quality control in real time with machine vision. And we end up with optimized lattice-based structures in the end. There are some benefits. So as other additive manufacturing process, there's no waste that is generated. Contrary to most additive manufacturing process, we can use basic materials. Contrary to powder-based additive manufacturing, where most of the energy has to be spent on getting the material that you can actually print, in our case, we can use byproducts out of the steel factory, if you want, which is just a metallic wire. The process in itself has a really reduced energy consumption, because contrary to wire arc additive manufacturing, we don't have to melt the whole structure. We just have to melt where we need to cut the wire, and we add energy where we need to weld it. So basically at the nodes of the lattice. We don't have supply chain problems because we rely on very common materials. again with very low embodied energy. We have an adaptive spatial resolution in the sense that we can cut the wires to the lengths that we want. So it's very easy to make dense meshes or much more sparse meshes for the lattice. So we can really optimize where we put the matter and how, we can optimize it. This process is enabling large-scale manufacturing of architectural materials. It's robot agnostic, and it's actually being considered for on-orbit manufacturing, which can sound like science fiction, but there's actually is a project at the moment to do that 5 years from now, with very considerable constraints, like for instance low energy. You cannot do WAM on orbit; it's too energy intensive. You have strong constraints on the materials you can use. Well, that's good for us, etc., etc. And it's a scalable process for industrial application. So basically, we improve the state of the art, which is today topology optimization combined with some kind of additive manufacturing process, for instance, for large structures, WAM. And so our aim is basically to surpass WAM for lattice manufacturing. So this is just a small video, because I know you want to see the process. So this is just 2 welding points at R&D speed. And this is done in our offices in Paris, so if you are in Paris, come visit us. Basically, our technology is based on the integration of very simple technologies by themselves, but put together. That's what the difficulty is. That's where the difficulty is. So basically, we use fiber lasers, common industrial robotics, machine vision, beam steering technology, and wire feeding and things like that. So we developed this tool that can be plugged on any 6-axis robot, and of course the software that goes with it. So just some figures about comparison, for instance, for a bracket design or for a bicycle frame. The idea is that we use less material than most conventional process, much less energy, and it costs about the same. Some examples. So I didn't mention, but the company was created in April this year. So 6 months, something like that. This is the first example. This is a nice body-centered cubic cell. If there are metallurgists in the room, you can see that the heat affected zone is very small compared to any other process I mentioned. So this is also good for the mechanical property in the end. Well, this is the same but with 8 cells. This is the same on a plate. Actually, I have the sample if you want to touch it. Just give them back to me in the end, please. There's 2 samples actually. There's a sphere that's not on the pictures that you can play with. And it's stainless steel, so you can go at it. This is some kind of an arch. And yesterday we did this, which is our most complex structure so far, with 283 struts or rods. So we're gaining up in complexity, and the idea is that, of course, in the end we can make lattices of lattices of lattices of lattices. Almost no weight in the end, and a lot of mechanical properties. So this is the future, right? This is what I'm here for, to tell you what's going to be tomorrow. So hopefully this process can actually be adopted by the industry, and we can create everyday products with this process in a more sustainable way. Talking about sustainability, let's make a car. So this is a lattice car that could be made using this process. This is like an airplane wing. And of course, since we are talking about construction today, truss structures have been used for quite a while in construction. The idea is that we can maybe make it better and faster and cooler. Yeah, there's some other advantages of lattice structures and architectural materials. Through geometry, you can also add function. And this is actually what I've been working for 15 years. You can, of course, play on this weight to mechanical property ratio. You can also control locally the mechanical properties. You can do damping, which is very important for industry. You can play on the Poisson ratio. You can improve acoustic performance. You can make better energy absorption. You can filter frequencies, etc., etc., etc. So yeah, that's our team. We're 7 now, and we'll be hiring very soon. And we don't have architects yet in the team, so if there are architects, looking forward to that. And yeah, just maybe to conclude on this slide, this is a very new process. It's only a few months old. There's no scientific literature on it yet. We are working on it. It's just a new way to process materials, making them more efficient and hopefully add multifunctionality, which again is something I've been guilty of talking about for 15 years, but you can't really see in industrial applications today. We hope that with this process we can actually reach that, and not just oversell a technology to basically redo everything that we know how to do very efficiently with a new technology. So Tetmet has been developing this process. It's patented, by the way. Hopefully it's going to be fast, fully automated, and it is frugal in terms of matter and energy. We are also working on a proper life cycle analysis, but our claims are quite well founded, I think. And this is without counting savings that can be done if we improve the properties of the products of our clients. So for instance, right now we are working with the space industry, and of course we can save CO2 on the amount of material and the amount of energy we spend to build the rockets. But if we can save, let's say, 50 kilograms, that's a huge improvement for the whole system. And this is not taking into account with my numbers, so it's actually even more, probably. There are applications also in construction, and one of the earlier adopters of this technology is actually Peri, which is a German company. I'm sure you know them. And we've been involved with them recently. And also some more traditional, let's say, risk takers in terms of processing technology, like Ariane Group or Airbus. And yeah, that's about it. So if you want to work with us, you can just click this link, take a picture, and we'll be happy to get back to you. Thank you very much.
Thank you, Justin. Are there any questions from the audience?
Thank you for this nice presentation. I was wondering whether there's also a new design tool necessary to create this kind of things. Are you working on that as well?
Yes. So our idea, since we are aiming for the industry, is actually to work with CAD software providers that already have the knowledge, that have lattices integrated in their software already. But of course, they've been developing all that for 10 years for additive manufacturing, which means gradients and nice shapes and all that. We have just straight lines, so it's actually both more difficult in the sense that the current tools are not adapted, but it's actually simple from our viewpoint because the geometry is very simple in our cases. So yeah, we are working on that, but we are counting a lot on our partners to co-develop that. And I'm meeting some of them this afternoon at Next.
Thank you. Are there any other questions? Yes?
Yeah.
My question is, right now we saw, for example, with this cube structure, So wouldn't it be, maybe it's a bit naive in the question, wouldn't it be smarter to just say, okay, I create like bends in the corners instead of melting all the corners? Because for me, what I saw was just welds in all the four corners of the cube. And if there are some of the points where you could just bend the wire instead of cutting it and then re-weld it. I don't know.
I'm not sure I understand the question.
So we have the cube,
Yeah.
and we have some of the connection points where you have like a straight 90-degree bend, for example. So wouldn't it be like possible to just say, okay, I take the wire, I bend it, and I only cut and
for sure.
weld it? Yeah.
It's okay. It's nowadays. I mean, this is again. We started in April with nothing. It's of course we can consider bent wires. It's it would have to be integrated in the whole tool chain, but it's not there's no technical limitation to do that. The thing is, right now the parts we are working on are structural components that need to be very stiff. And if to start with you have bending in your struts, it will be less stiff than a straight bar, just because of the, bending stiffness is lower than compressive stiffness.
I was asking about the corner connections, where you just say, okay, if I have a 90-degree bend and I weld one to it, I have like a 3-point corner instead of welding 3 times for the three studs.
Okay, yeah, it's possible. It's actually your question is very interesting because it's a real problem to put all those struts together. 2 struts is easy, but we can go up. We have been going up to 32 number of connectivity, so 32 struts in one point. It's a real challenge to do that.
Thank you. Are there other questions?
You might have answered it already with the first question about the software, but with additive manufacturing, we have slicing software that kind of tells the laser what to print at every line.
Yeah.
Do you have your own software to know which rods to put first?
Yeah. Yeah, so we have those building strategies like you have in additive manufacturing, except that in our case it's not like a tool trajectory in a plane. In our case, it's really a vectorized space with. We have a model of all the rods in the structure, and then it's just an iterative process with some optimization, of course. Yeah.
Thank you. I have also a question. I was wondering if you could say a little bit more about the construction applications and the scaling up strategies in that case. Is the idea to have a huge more amount of rather small pieces? Is it about scaling up those pieces directly? And my associated question would be, how does it affect sourcing in the construction industry? Because I'm guessing the metal doesn't come from the same places than aeronautics.
Sure. So I cannot disclose anything about the construction application we have with Perry, but we have ideas about how this could be used. For instance, we could imagine, creating some kind of architecture, the wall with lattice as a structure and then insulation foam, like people have been doing for 3D printing of concrete. We could also use that as a rebar for concrete additive manufacturing. Maybe, I don't know. And what I can say is that with all those partners, we have development projects on very specific use cases. And the idea is that those use cases are realistic and that we can do them in a few months. So it's not a building. It's not a building. It's and we haven't thought yet of the scaling of that. But hopefully, with our partners, we will discuss that together. But we also we are developing a technology that's very specific. We have about no knowledge of the construction industry, the real construction industry. So we prefer to be in partnership with experienced actors for that. So, for instance, Perry.
Thank you.
Thank you.
Are there other questions? Yes.
If you have more number of struts coming to a common point, you'll have more number of welds. What effect will it have on the strength of the part? Of
the part or of the lattice node?
Yeah, eventually the part, I believe.
Okay, so then it's a really valid question, and this is the same question. You can ask the same question for metallic structure in general in construction, but the advantage of having such a fine lattice control is that you can have redundancy of nodes. So of course the weld quality is it's our first priority actually. More than anything else I presented, it's if we cannot reach the weld quality of traditional welding, it's not even worth trying, because I agree it will fail at some point. But the good thing is that we have AI to help us in that endeavor, and also we have research project with academic labs, my lab, to work on the metallurgy of the process, and we do have a project currently to study, make a proper metallurgical study of the welding joints. And of course, if you weld and re-weld a node, you will change the phases in presence, you will change the properties, but so happens in additive manufacturing. So the worst case scenario is that we are as bad as additive manufacturing, and I think we are much better because we have very small heat affected zones. So that's my gut feeling as a metallurgy professor, but this needs actual characterization and confirmation, and we are working on it at the moment.